Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but still want to be its friend.
Yes, me included. And I'm Corinne Caputo, a writer, fun person, and a friend to the universe.
You most certainly are, and a friend to me.
Yes.
Hi, everyone. I'm Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and a good bud to the universe. Mm-hmm. Mm-hmm. It's a great time in the universe to be alive, one where it's small enough that we can still see stuff, but big enough that it's not too hot for us to exist. Like, the universe is really looking out for us right now.
Yeah, I feel like time's running out on that, so it's good I got in now.
Mm-hmm, yeah, we only have a few, like dozen billion years left.
Yeah, exactly.
That's it. But while we are contemplating the long-term fate of the universe, we are sitting... I'm sitting on the ground, and it's hard and it's rocky because we are in a canyon. We're in a canyon in New Mexico.
Yeah.
It's majestic. Is that a word you would use to describe this, Corinne?
I would, because I feel like I'm always at a loss for words with, beautiful nature things, you know?
Mm-hmm. But it's, we are at the bottom of this canyon. We can see it rising pretty high above us. All that beautiful, brownish, reddish stone. Mm-hmm. The wind whistling through the canyon. It's like I feel one with nature right now.
Yeah, me too. I love being outside.
Mm-hmm. Yeah, and, we are going to be in the American Southwest for a couple weeks.
Yes,
we're doing a brief tour of New Mexico, both real and fictional, this month. So yeah, let's get into our episode.
Yay.
While we're sitting here in this canyon. Today we're talking about supernovae.
Yay!
Yay! Corinne, thoughts? Feelings, comments.
I'm pretty sure that supernovae, is the plural.
Nova is singular. Novae is plural, or novae, or novae maybe. Supernovae. I have never heard that. Supernovae is what I say.
Supernovae. It's when a star explodes, right?
Yeah, that's one way that you can get them.
Oh, there's more than one way. I didn't know.
There's more than one way. I mean, I guess, yeah, technically all of them are like explosions that are around stars. You do need a star to make a supernova, but there are multiple types of supernova, and we'll get to that later in the episode.
I can't wait. Yeah, so I think of it as a really huge explosion that is exciting and rare and far away from us experiencing.
Yes, hopefully.
Yeah.
Hopefully far away from us experiencing. We do not want any supernova explosion happening close to us.
No.
I'll say up top, these supernovae are really powerful explosions. One single supernova, and they range in strength, but like an average supernova will put out as much energy in a brief period, maybe as short as a day, the same amount of energy that our sun will produce in billions of years through fusion. So they are very powerful. They give off extremely dangerous radiation, like high energy radiation, like X-rays and gamma rays. That radiation, if it was emitted close enough to us, it could ionize our atmosphere. So change the actual particles in our atmosphere and remove electrons from them or add electrons to them. It could do a lot of damage. So we don't want any supernovae close to us. But luckily, there aren't any stars nearby that will go supernova anytime soon.
Amazing. I love hearing that.
Yeah.
This has nothing to do with me, and I can just learn about it.
Exactly. Yeah, I wanted to get that existential fear out of the way at the top of the episode because supernovae, very cool, very dangerous, but nowhere near us. So we're
Ideal.
Good. We're safe. Yeah. I want to talk about the history of supernovae because even before there were telescopes, people were observing supernovae in the sky, even though they didn't know what they were. Because a supernova, when it goes off, it just looks like a new star has appeared in the sky, like a new, very bright star. Some of them bright enough to see in the daytime.
Whoa, that's freaky. That would, especially in the faraway past, that would have really freaked the people out, I assume.
Oh, yes. Oh, yes, it did. There's a lot of mythology and folklore wrapped up in supernova. You know, what would make a new star appear in the sky? Are the gods trying to send us a message? And there's so much there that I'm going to break from Moiya tradition and not really talk about the folklore of supernovae, and instead just talk about the confirmed ancient supernova observations. Thousands of years ago, people would take note of these things in the sky, and some of those records survive. But the oldest known record is only from 185 CE or AD, so like 185 of our years right now. That's like a weird concept to explain because time is weird.
It is.
But it's very likely that older supernovae were observed. We just can't confirm any records of them.
Oh, okay.
So that earliest one was observed in the year 185 by Chinese astronomers, and they noted that a bright star appeared in the sky for 8 months near the constellations that we currently call Circinus and Centaurus. That is not what they were always called, and that's definitely not what Chinese astronomers called them.
Yeah.
They had their own, like, very cool constellation system.
Yeah, it seems like a Greek or Roman name for sure. Or like some kind of modern name. Yeah.
And we talked in our constellations episodes about where these names came from. Both of these are in the southern sky. And so there was this historical codex that was written in the 4th century, in the 300s. Note, that is like 200 years after this supernova is meant to have gone off.
Yeah.
So like 200 years later, someone writes in this historical document that survives, which probably means it was written in another document that didn't survive. But this historical document is called the Book of Later Han, and it says, quote, "A guest star appeared in the middle of the southern gate. The size was half a bamboo mat." I would love to know how big a standard bamboo mat is.
Wow, that is half a bamboo mat.
It was half a bamboo mat. It displayed various colors, both pleasing and otherwise.
And otherwise. Some of them I hated, and I won't name which.
Yeah, some of these colors were ugly.
And they know who they were.
I don't have to name names. They know. Both pleasing and otherwise. It gradually lessened. In the 6th month of the succeeding year, it disappeared. End quote. They also noted that this guest star did not move across the sky like a comet, so that helped them rule that out as an explanation. And instead, it was fixed in the sky. We have been able to confirm that this was an actual supernova because supernovae, most of them, leave behind remnants. They leave behind a little, a message, an echo, a reflection of their former exploding selves. And scientists were able to find the remnant that was left over by this supernova. So they took observations with modern telescopes, and they found this shell-shaped cloud of gas. It's like a nebula. It is a nebula. So if you've ever seen pictures, those multicolored pictures of gas in space, like that's a nebula, and that's what this is. That nebula that they found is called RCW 86. RCW is a catalog of regions in space that are emitting a lot of hydrogen, like these molecular clouds with a lot of hydrogen in them. And RCW 86 was in the same position as that supernova that the Chinese astronomers took note of. It's the same distance away, or like the right distance away for them to have seen the brightness. So it's about 8,000 light years away from us. And it's roughly the right age. They can measure how long ago a supernova would have happened by measuring how big the shell, like the supernova remnant is, because the shell moves over time. And so they can just like work backwards to figure out how far has it moved and how long has it had based on its current rate of motion.
Oh, cool.
And they have observed it in the X-ray and in the infrared, and both of those observations, based on like the spectral analysis of it and comparing it to other nebulae, it suggests that it was a type 1a supernova. And I know I haven't explained what a type 1a supernova is, but we are going to get to the types in a bit. For now, let's just say that this is the type of supernova that happens when two stars are orbiting each other.
Okay.
Like some supernova happen because of two stars working together, and then there are other supernovae that just happen because of one star exploding.
Okay. Ooh.
Yeah. There were two more supernovae that were recorded by 4th century Chinese astronomers, but they have not been confirmed by modern observations. But it seemed like the year 300-ish, or like that century, was quite big for supernovae in the Milky Way. And then nothing happened for almost 1,000 years, or at least nothing was noted for almost 1,000 years in terms of supernovae, until the year 1006. This is, or was, one of the brightest supernovae ever recorded, if their observations are to be believed. So in 1006, a supernova was observed in the constellation Lupus, and it was observed around the world. So, like, pretty much the entire globe could see this. An Egyptian astronomer, Ali bin Ridwan, wrote, and I quote, "The spectacle was a large circular body 2.5 to 3 times as large as Venus." And Venus was a good benchmark for them because it's the second brightest thing in the night sky after the moon. People had been studying it for a really long time, and it's like a good reference, a common reference point that everyone back then would have known. So it looks much bigger than Venus. It's brighter than Venus.
That must have been big.
Big, yeah. The sky was shining because of its light. The intensity of its light was a little more than a quarter that of moonlight.
That's very bright.
This interestingly appeared to have 2 peaks in brightness. Usually a supernova will have like 1 peak and then it dims. But this had 2 peaks 18 months apart. And that is indicative of 2 white dwarfs merging and each of those kind of going supernova in their own time.
Oh, okay.
Yeah. So, like, it's really helpful that we have records from this from all over the world, Roman astronomers, Chinese astronomers, Egyptian astronomers, because they saw it at different times and they, like, took different notes. So that's how we know that it had this double peak feature, which is really cool.
I love that.
Yeah. And then later that century, again, another century that is pretty rife with supernovae, in 1054, this is maybe the most famous supernova ever.
Ooh.
Yes. This was also noted by astronomers around the world, and it was even depicted in some indigenous art in North America. And so one place that it was depicted is right here in Chaco Canyon, in a cave painting in what is now New Mexico. And the cave painting shows like a hand and then maybe what could be a moon and then a bright thing that could be the star. And they think that maybe the moon is there in the painting to show that the two things were close.
Yeah.
Like the new star in the sky and the moon were close. And astronomers have worked backwards to figure out that at that time, the supernova in that position in the sky would have been very close to where the moon would have passed by.
Oh, cool.
Yeah, so we are at that site right now, or very near it.
I love that these were seen around the world and everyone's talking about it. The first viral thing.
Oh my God, yes! Supernovae were the first viral space memes.
Monoculture, yeah, exactly.
It was really bright. It was seen in the sky for 2 whole years, which is why so many people around the world took note of it. And we know for sure that that was a supernova because we have found the remnant it left behind, and that remnant is the Crab Nebula, which is one of the most studied nebulae in the night sky.
We've talked about the Crab Nebula.
Yes, we have, because it has the Crab pulsar in the middle. So the star that exploded to make that supernova then collapsed into itself, formed a neutron star, which became a pulsar, and now we study the Crab pulsar at the heart of this nebula.
Beautiful. I
love when that happens. All of our episode topics coming together.
Yeah.
It's like the Justice League of science communication. I don't know. And then in 1572, so this is like over 500 years later, there was another supernova that was recorded by Tycho Brahe. I was about to say, like, maybe we'll do an episode on Tycho Brahe, but, like, probably not for a while.
Mm-hmm. He's still alive.
He is, but his nose isn't.
Yeah.
I have a stuffed brain, like it's a plush brain. Mm-hmm. And I named it Brahe the brain, because it also doesn't have a nose. So
I don't know what this person looks like. Let me find this out.
Oh, Tycho Brahe was this very successful astronomer in the 1500s,
Oh, yes.
and he lost his nose in a duel.
Oh, no.
He like challenged someone to a fight, and they cut off his nose.
That's like my nightmare. Ugh.
I know.
And he has a huge mustache. Was that to balance out the nose?
The lack of nose, maybe. But he had a prosthetic one. Like in most images I've seen of him, he's wearing like a metal nose.
That part's cool.
Tycho Brahe is some interesting person with an interesting past. Anyway, he wrote a whole report after he noticed this supernova in 1572, and the report, I think this is Latin, and it's De Nova et Nullius Avi Memoria Prius is the name of the report. That translates to concerning the star, new and never before seen in the life memory of anyone.
I'm loving the terms that are coming out of this. We got guest star. We got never before seen. Marketers are still using this today.
You're right. You're right. Actually, another term that comes out of this is nova. Before, people were just calling them new stars or guest stars, and then Tycho Brahe comes along, calls them nova or novae, and that is the term that astronomers use for the next 500 plus years to describe like a star that is brighter than it usually is. So he noted that this new guest star or this new nova didn't change its parallax, so it didn't appear to move in the sky, which meant it must be really, really far away. Like it must be outside of Earth's atmosphere, even farther away than the moon, because at the time the leading belief was that everything outside of Earth in the universe is still. That it's perfect, it's static, and that Earth is the only thing moving. And so when Tycho Brahe pointed out that these stars are way too bright and they must be elsewhere, that really challenged the way people thought about Earth and its relation to space.
Yeah.
So good for him.
Yeah.
Yeah. That's 1572. And we then see another supernova in the early 1600s that Johannes Kepler writes about. But then we don't see any supernovae for a really long time in the Milky Way. The 1600s, we invent telescopes, so we start seeing further things, and we notice a lot of supernovae in other galaxies, even though we don't know that other galaxies exist until the 1900s. So it's a very messy time in astronomy history where people are really just trying to figure it out. We started to figure it out, to figure out what is causing these new stars to appear in the 1800s. In 1866, a scientist named William Huggins was studying the first spectrum of any nova. But this was a special type of nova called a recurring nova, which I had actually never heard of before I did my research for this episode.
Oh, whoa.
Yeah, so I'm learning stuff, friends, which
That's
is great.
what it's all about. That's why this podcast exists.
So that I can learn.
So Moiya can learn.
Yes. A recurrent nova is a kind of rare type of system. We've only found maybe 10 of them. It's a binary system where one of them is a white dwarf, and the white dwarf gathers material from the other star onto its surface, and that extra material just like gives it a little bit of energy, so it like burns at the surface and gets brighter than usual. And it happens over and over again as the star gathers more material. So you would see like every 100 years or so this star get brighter in a flash and then dimmer again.
Oh, whoa. Okay.
Yeah. So we knew about these recurring novae. William Huggins was studying the spectra of them for the first time, and he suggested, based on what he saw in the spectrum, that a stellar explosion was responsible for these stars that get brighter than they should be every once in a while. And just the fact that he called it a stellar explosion got other astronomers interested and excited, so then they started paying more attention to these types of stars, because they were dudes who like to blow stuff up or see other things get blown up in space.
Yeah, a trend that exists today.
And so 1866, we study the first spectra of a nova. And then in the 1930s, we started being more intentional about that search. In the 1930s, Walter Batty and Fritz Zwicky, two scientists who we've talked about before, two scientists with absolutely chef's kisses of names, I believe, they distinguished novae from supernovae after they were going back in the catalogs and they found this one. It had been categorized as a nova before, S Andromedae. So it's this bright spot that appeared and then disappeared in the Andromeda constellation. It was discovered in the 1880s, and even then, they knew that it released more energy than the sun produces in millions of years. So they noticed that it was a lot brighter than any other type of nova that they had seen before, so they called it a supernova because it was super bright.
Creative. Love it.
So creative. And then in 1933, Fritz Zwicky started the first supernova patrol, where he was systematically going through records through these plates that have pictures of the sky at different times, and he was looking for changes. You know, like if you look at the same patch of sky, is there a star there one day that is gone the next? And after doing that, he found about a dozen supernovae in 3 years. It's a lot of work.
That is a lot of work for not, I guess, more. But a supernova patrol is the funnest name for, like, a little gang of people that I've ever heard. Like, I want there to be a kid's show about space, and it's called the Supernova Patrol.
Like, what if Paw Patrol wasn't police propaganda, but was instead about a bunch of animals looking for supernovae?
Yes, exactly.
Be so fun.
And they're all like little different kinds of scientists. They can still be puppies.
Oh, yeah. Oh, I love that. We have a little puppy astronomer and a little puppy chemist. And
Maybe this idea is too good. Dibs on this idea. Moiya and I are calling dibs on this idea.
TM.
Hey friends, it's Moiya here. I am actually the one on the move today, so I apologize if the audio is terrible, but I just couldn't pass up the opportunity to explore this canyon and search for that supernova painting. But while I walk, let me say thank you to all of our amazing patrons who support the show every single month. We could not do the show without you. Well, we could, but it would be worse, and Corinne and I would go into debt. But thank you, as always, to our sun-like stars, Sharn Llewellyn, Lissa, and Peyton. I hope the hydrogen you are munching on today is extra tasty. And a big welcome and thank you to our newest pre-main sequence star, Eleanor Mulshine. What a beautiful name. Welcome to our stellar club. You too can support us, hear your name on this pod, and make it to our patron star chart, all by supporting us on Patreon for just about $1 per episode. And if you sign up for an annual membership up front, you get a 13% discount across an entire year. That is 1% for every constellation in the zodiac, because we love Ophiuchus over here. Find the star chart, our Patreon info, and more at our website, palebluepod.com, or you can go right to patreon.com/palebluepod. We would really appreciate your support. But if you can't give financial support, that's totally fine. You are still space, and we love you. There are other ways to support us. You can review and rate the show on whatever app you use, or you can share the show with your friends. So pick your favorite episode and send it to someone who you think might like it. And we will be eternally grateful. So you probably know that Pale Blue Pod is a part of a collective of independent podcasts called Multitude. And Multitude, as a group of indie shows, exists because of the support of listeners like you. The best way that you can support Multitude is by joining the Multi-Crew, which is our membership program that lets you, our listeners, help to fund new work from Multitude and get exclusive perks. That's why, from now until October 1st, we are running the Multi-Crew Drive. We're putting 2 weeks aside to highlight the ways that your support makes a difference to us at Multitude and how that support gets paid back to you, our community. Our goal is to add 100 new and upgrading members to the Multi-Crew by October 1st. By joining the Multi-Crew for as little as $5 a month, you can get some amazing perks like exclusive audio content, access to our Multi-Crew only channels on Discord, where we have a lot of very fun gatherings and game nights, and so much more. So here is how it works. Anyone with an annual plan by October 1st will be immortalized on our We Put 2023 on Our Back plaque. Annual plans are particularly helpful to Multitude since we can count on a whole year of support instead of varying month to month. So we really want to thank our annual members in particular at every tier with these new perks. Plus, our annual plans have a special discount. You get 2 months for free when you sign up for the year. So to join the Multicrew, head to multicrew.club to sign up for your annual membership before October 1st, 2023, and receive amazing perks plus our exclusive mug and be immortalized on our plaque. Remember, you can sign up for an annual membership at multicrew.club to join the Multicrew, and you will not be disappointed. Finally, Corinne and I can hardly believe that we are nearing our 50th episode, almost a whole year of Pale Blue Pod. My mind is blown. To celebrate, we really want to put together a special AMA episode, that's Ask Me Anything, for those who aren't chronically online. And we want to answer your burning questions about space, the universe, and our relationship with it. So if you have a question, please email palebluepodcast@gmail.com, or you can message us on Twitter, formerly or X or whatever, or Instagram. Our handle is palebluepod on both. And I cannot wait to hear from you and answer your questions. I really want to see what you're curious about because this show is for you. All right. I am almost near the painting, so I'm going to check that out, and then I'll meet Corinne to make the rest of the episode. But thank you for listening, and let's talk about some supernovae.
So really the idea that supernovae are explosions came in the 1860s based on spectra, and then we just ran with that, and it ended up being right. And so in the 1930s, we started studying a bunch of these supernovae that we could find. We started finding a bunch of them in other galaxies, now that we knew other galaxies actually existed. And then we were able to classify them. Astronomers, humans in general, love to classify things. If we find enough of a certain object, we are going to try and look at the differences between those objects that we've identified as being the same thing. For some reason, that's what we do. I don't like it, but it's what we do. And so we classify supernovae by their spectra. Broadly speaking, there are two classes. It's split up into type 1 and type 2. Type 1 supernovae have absolutely no hydrogen emission lines in their spectra. They are devoid of hydrogen, whereas type 2 supernovae do have hydrogen emission in their spectra. We really care about hydrogen, so that's how we delineated. And these categories were made before we understood how supernovae actually happen, and I am convinced that had we known back then, our classification scheme would have been different, because with the knowledge I currently have, this makes no sense. So let's start with the type 1 supernovae. There are 3 subclasses of type 1. There's type 1A, type 1B, and type 1C. Okay. Type 1A supernovae happen when you have 2 stars orbiting each other and one of them is a white dwarf. This is what we think that first supernova in 185 was. So you have 2 stars, one is a white dwarf, and white dwarfs are really massive, even though they're quite small. A white dwarf is typically around the mass of our sun, but about the size of our moon. So they're small, but they're dense. So they have a very strong gravitational field.
I was just going to say that.
Yeah, Corinne! Your intuition for space stuff has gotten so much better in the last 45 weeks.
I know. We're coming up on a year.
We are. I'm so proud of you and us.
And listeners.
And listeners, too. Yay. Oh, maybe we should put out, like, a little quiz for our listeners to do of all the stuff we've covered. All right, we'll think about that.
Including facts about our lives.
Yeah.
Including any personal thing we've referenced on the show.
Which one of us is a twin?
Yeah, exactly. That was going to be the question.
One of us is a twin and likes smalls. Which one is it?
There's one answer.
So they have a very strong gravitational field, going back to white dwarfs. And that extra gravity means that they can actually rip away material from the other star. It is the hungry, hungry white dwarf, and it is stealing the body of the star next to it. And once it steals enough, once it gains enough mass, it reaches a point where it's dense and hot enough to fuse carbon and oxygen in its core. And that is actually an unstable type of fusion because it creates this really extreme gradient of temperature and density where you have high temperature but low density in the core, and then low temperature but high density on the outer layers. And at the place where they meet, it creates an unstable chain reaction because it creates this like churning at that interface. It creates a lot of mixing, and that mixing increases the like burning rate in the star so much that it explodes. Like it gets too hot too fast and then it explodes is basically what happens once you start fusing carbon and oxygen. It's called carbon detonation, and there's an article about it in this week's research notes if you subscribe to our Patreon.
Yay.
Yay.
This reminds me of once I went to a restaurant and it's not quite the same, but they had, I guess a glass had just come out of, why would it be the same? A glass had just come out of the dishwasher and it was like still really hot, and then they put like my water in it and like put it down and the glass exploded.
You know what? That's not far off.
Yeah.
That's really actually not far off.
It was just like the temperature change suddenly made an explosion.
Yeah, absolutely. I think that's a perfect analogy, Corinne, because it's really when these super hot things meet a very cold thing that you get cataclysmic stuff.
Yeah, and it can happen at the restaurants now.
It can happen anywhere.
It can happen anywhere.
That's what Pyrex was invented for.
Yeah.
Really.
Thank you, Pyrex.
There's this really cool consequence, this really cool thing that we can use specifically type 1a supernovae for. Because these supernovae are caused by stars with roughly the same mass, it's at about 1.4. I say about, but like we've really narrowed it down. It's like at 1.4 times the mass of the sun. That is when a white dwarf will reach this carbon detonation limit and explode as a supernova. And because it all happens around the same mass, they are roughly the same brightness. And the very little variation in brightness can be removed if you look at the relationship between the peak luminosity, so like the max brightness that the supernova had, and the decay rate. So how long does it take the supernova to get really dim? Brighter supernovae dim faster than dimmer supernovae. If that makes sense. Yeah. Okay. And so if you use that relationship and you figure out like what the peak brightness of the supernova was, you can use these as what we call standard candles in astronomy. And a standard candle lets you measure really big distances. Imagine you have a light bulb and you know the wattage of the light bulb in a dark hallway. As you move away, you can measure how bright the light bulb looks to you, and it's going to seem like it gets dimmer as you move farther away, but the actual brightness of the light bulb is not changing. And so we kind of use these supernovae as that light bulb. We know how bright it should be inherently, and we know how bright it looks to us, so we can calculate how far away we are from the supernova.
Oh, okay, cool.
Great.
I love that.
Yeah.
I love when we use context clues.
Yes! This is actually, like, measuring distances is really important in astronomy because it's that third dimension is not as easy to see, and sometimes space plays tricks on us where things seem closer than they are because of gravitational lensing. And so like we really care about figuring out the distances to objects, and we have devised this very complex system of techniques called the distance ladder. So you use some techniques like parallax for short distances, things that are close to us, and then you might use a standard candle for something that's in a galaxy, like in the next galaxy cluster over. But by the time you get to really big distances, then you have to use something like cosmological redshift to measure the distance.
Okay.
Yeah. So now we've talked about, I think, 3 rungs on the distance ladder throughout all of the Pale Blue Pod episodes. We've talked about parallax, we've talked about cosmological redshift, and now we've talked about standard candles. Yay. I also have a whole chapter on the distance ladder in my Milky Way book, so you can go read it up. That's type 1a. Type 1b supernovae were distinguished from type 1a in the 1980s, and the main difference here is that their spectrum shows helium emission, but no hydrogen emission and no silicon emission. So yes, helium, no silicon, no hydrogen. Whereas type 1c supernovae, also distinguished in the 1980s, they show no hydrogen, no helium, and no silicon. So it's essentially just like 3 different steps on the timeline of a star that shows when they exploded. Like the type 1c supernova exploded when the star was out of hydrogen, helium, and silicon, but a type 1b supernova exploded when there was still a little bit of helium in the atmosphere of the star.
Okay.
This is my issue with it. This is where we get to my gripe. Because type 1b and type 1c supernovae are not caused by 2 stars orbiting each other. Like, it is not the same mechanism as a type 1a.
Yeah.
Both of these types are formed through the same mechanism as type 2 supernovae. But they are
so
type
why
1.
did they put them in
Because
B
it's
and C?
based on the spectrum.
Oh.
Yeah. So let's talk about type 2 supernovae, because I think they're usually what people think of when you hear the word supernova. And so they are also called core collapse supernovae because they are what happens when a massive star collapses at the end of its main sequence lifetime. So after a massive star, and I'm talking stars that are more than, let's say, 10 times the mass of our sun. The cutoff is a little fuzzy. Some people would say 8, but let's just round it to 10 times our sun's mass. When a star that massive runs out of fusion in its core, it can no longer maintain its shape, because a star is maintained by something called hydrostatic equilibrium. That is the buzzword of today's episode. Hydrostatic equilibrium basically just means that the force of gravity pushing in is balanced out by the force of radiation from nuclear fusion pushing out. So you get this balance. But when there's no more fusion, there's no more radiation pushing out. So gravity is able to just win, pulling itself in. But let's talk about that fusion, because fusion's really interesting. It starts, as all stars do, by fusing hydrogen into helium in the very core of the star, like the center of the star. And then you end up with a core of helium because you have turned all of the hydrogen into helium. But you can then fuse that helium into even heavier elements. So you fuse the helium into carbon, and then you have a little shell of carbon, which you fuse into oxygen. And then that core of oxygen gets fused into neon, which then gets fused into magnesium, which then gets fused into silicon. And then the next one up would be iron. But you cannot fuse iron in the cores of stars because it takes more energy to fuse that reaction than it produces. And stars and everything else in the universe are lazy. They don't want to do something that like takes more energy than it's going to produce. It's like, you know what it is? You know what it is, Corinne? Fusing iron for a star is like us eating celery because it takes more calories, it burns more calories than it gives you.
Yeah. And only people with a likely unhealthy relationship to food are like, I gotta eat that.
You're right. You're right. So once it gets to the iron stage, it stops fusing, and then you have these layers. So in the middle would be iron, and then it goes backwards. So the next layer is silicon, then magnesium, neon, oxygen, carbon, helium, and then you have this shell of hydrogen on the outside, which is why the spectrum of a type 2 supernova shows hydrogen, because all of the hydrogen is left on the outer edges of the star. It has this shell effect. So the fusion stops, gravity creates this implosion, it hits that like iron core, or maybe it just hits like the carbon and oxygen core, and then it rebounds out as a supernova explosion.
This feels like one of those large Jawbreaker candies that have like the layers of color inside, except there's no explosion when you get to the middle.
You know, I don't know this to be true, but I would not be surprised if those Jawbreakers were not modeled after, like, you know, the layers of the star, or the layers of Earth and, like, the mantle and the crust and everything.
I hope they were, and I hope teachers give them out during this unit.
I mean, that's what I would do. If I were teaching about fusion of massive stars, I would absolutely give out Jawbreakers.
It's good to have a little treat. Yeah.
One day maybe. Type 2 supernovae, they are also subclassified, but they are subclassified by the shape of their light curve. So how much light is the supernova giving off over time? Some of them drop off immediately. They have this linear dimming effect, whereas others have kind of a plateau, and they're like the same brightness for a little bit, and then they drop off. So that's like, the first one would be type 2L for linear decay, and then the other would be type 2P for plateau and then decay. Generally speaking, these type 2 supernovae, regardless of the shape of their light curve, are dimmer than type 1A supernovae, which is why they are not used as standard candles, and why we cannot see type 2 supernovae from very far away. Like, most of the far-reaching supernovae that we see are going to be type 1A. Any questions about types?
I don't think so. I think I get it. I think it's funny to call it type 2, like, P, because to me that implies that there's an A through, like, LMNO. But I get it. I get it.
It does imply that, especially since it's type 1 ABC.
Especially because 1A went ABC.
Yeah. See, this is what I'm saying. Classification schemes in astronomy are a clusterfuck. It's a shit show. Like, we make up whatever classification scheme seems most convenient at the time with total disregard.
Okay, but it's so
for
relatable.
What has come before.
It's like exactly how I label every document on my computer. I'm not, there's no process. It's just like final, this one. Like,
final 2, final this time I mean
final
it.
revised. Yeah.
Yeah, astronomers are just people.
They're just
making
people.
up systems
Process,
to understand the universe. Yeah. Yep.
I get it.
So that is what we have learned about supernovae in the last 2,000 years since we found the first one almost. But why? Like, why do we care about supernovae? What can studying them tell us about the universe? And I have broken this down into like 3 different sections. Studying supernovae helps us understand, first, the origin of heavy elements, second, the evolution of stars, and third, the evolution of our entire galaxy. So starting first, the origin of heavy elements. We know that elements up to iron can be produced in the cores of stars. We know that now. And then we know that the supernovae will spread those elements out into space, into the space between stars that we call the interstellar medium. But we would like to know, what exactly does the fusion process look like leading up to the iron stage? We want to know how efficient is a supernova at spreading these heavier elements throughout space. And now that we have studied gravitational wave producers, we know that like the even heavier elements are made in those really energetic explosions or collisions. For understanding stellar evolution, we are kind of unclear on what happens after the fusion stops, but before the supernova is over. And we're really not sure what makes a supernova, especially like a type 2 supernova, what determines the shape of its light curve and how long it stays lit, because we know that relationship for type 1A supernovae. We know that a brighter supernova will dim faster for type 1A, but we're not totally sure for type 2. And then for galactic evolution, there's a lot here. We want to know how common the supernova explosions are in our galaxy and in others. We've observed rates in other galaxies, and we understand, or at least we think we understand, how often stars form in the Milky Way, and that should let us simulate or model out how many of those formed stars should become supernovae. And so we know that we should see about 2 to 3 supernovae per century in the Milky Way, but we haven't. We haven't seen one for over 400 years. Yeah. Although there was a remnant found for a supernova that should have gone off like 325 years ago, but it wasn't observed. So we're not sure. But like there was for a while this problem, this question of like, why aren't we seeing all these supernovae explosions in the Milky Way? And it turns out that it's probably just because the supernovae are happening in parts of the galaxy that are obscured by dust. They're happening in the disk, they're happening closer to the center, so we physically just can't see them, especially if they're dim type 2 supernovae. Mm-hmm. But we are pretty sure that the supernovae are still happening because they give off gamma radiation. We have measured the amount of gamma rays that are just kind of like present in the Milky Way, and it does seem like they're being replenished by supernovae. It's matching the expected levels of gamma radiation, but we just can't see them. Yeah. So it would be nice to figure out how to see them so that we can confirm the supernova rate. It would also be really cool to study more of the winds that supernovae produce. They create these like walls of particles that move through space, and that's like a wind. And these winds can have an effect on their environment. They are responsible for taking those heavy elements and spreading them through space, thus increasing the metallicity of the galaxy on average. Metallicity is like how many elements are heavier than helium here. These winds can move gas around so that it collides and then makes new stars, but the winds can also change the temperature of a region. If it cools the region down, then yay, new stars. But if it heats the region up, then oh no new stars? Like, space is really complicated.
Yeah.
So we would like to know how many of these winds are making new stars versus quenching star formation is the way astronomers would put it. And then we can also understand universe evolution. We can study the expansion of the universe and the behavior of dark energy by studying type 1 supernovae as the standard candles that they are. There's a lot of reasons to study supernovae.
Yeah.
They're cool. They tell us about lots of stuff in space.
Yeah, they feel like these secret keepers.
Ooh, I like that. Supernovae, the secret keepers of the universe.
That the supernovae patrol will get to the bottom of.
They will. One of them is a detective, not a cop, but a detective, like a private eye.
Yeah, exactly.
We have come up with cool ways to study supernovae. They're transients, so they're like in the sky one moment and gone the next. So you have to act really fast if you happen to detect a supernova. I think I've talked about this on the pod before, but I had a professor in college who studied supernovae, and one time we were in lecture, like he was in flow, talking about cosmology and the expansion of the universe, probably. I don't know. But he got an alert on his pager that a supernova had gone off in some other galaxy, and he was just like, all right, class dismissed, gotta go check out.
You gotta call it.
Supernova. Yeah. So class was over, and then he went to check out the supernova.
That's a family emergency. Like, that's like, I have to go.
Look, when you are in the supernova patrol, a new guest star appearing, that's an emergency. You gotta urgently go look at that. So we've put together surveys of the sky, just looking across the sky to search for remnants, and we do this in a systematic way, search this region and then that region, and like make sure you scan every bit of it. And that is a good technique to look for these transient objects that are there one moment, gone the next, because if you scan the sky multiple times, you can compare the images of an area over time. These surveys are really great opportunities for like citizen science projects or amateur engagement. There's this thing called the Cosmic Cataclysm program, where you can help scientists identify supernovae and their remnants by combing through data with your eyes. And that's just like way more human labor than the field of astronomy can produce, and so we need other people's help. There was even a supernova found in May of this year, May 2023, by compiling observations from more than 1,000 amateur astronomers around the world. And so, like, you too can get involved and help find supernovae. You can be part of the supernova patrol. And then I and other astronomers, I'm sure, are very excited that we're going to get an instrument in 2026 that should be able to find supernovae pretty much in real time. So the instrument is called the Ultraviolet Transient Astronomy Satellite, or UltraSat for short. And it's a multinational collaboration headed by Israel with a lot of NASA support. So NASA's going to launch it and also provide a lot of operational support. and like science support. And it features a wide field of view, so it can see a lot of the sky at once. Advanced ultraviolet sensitivity, which means it will be keyed in, it's primed to see ultraviolet light, which is a type of light that supernovae give off a lot of. And it has real-time data control and transfer. So this telescope, as soon as it sees an ultraviolet transient object, will immediately transfer that data down to Earth, and we'll be able to look at that spot in the sky with other telescopes.
Cool.
Yeah. I think anything else that I could say about supernovae would be like so deep in the weeds, like stuff that previous guest, almost Dr. Serafina Nance, studies, like what specifically are the spectral differences between these types of supernovae. So I think that's like everything that anyone needs to know about supernovae.
Yeah. That's cool. They seem great. I want to see one in the sky.
Yay.
Paint a picture of it. I did throw in a funtivity.
I see that.
Which is just...
What's your last hurrah?
What's your last hurrah? Okay, because on, NASA has a page online that's, kind of for kids, and it just gives, really overview stuff of cool space things, and it says, one type of supernova is caused by the last hurrah of a dying massive star. This happens when a star... at least 5 times the mass of our sun, goes out with a fantastic bang.
So, Corinne, do you want us to think about our last hurrahs?
I was like, what's your last hurrah? Okay, it sounds very dark, but
yeah.
What I'm thinking is it's just what's your dream party?
Ooh. I like this. I mean, you're right. It does not have to be the last hurrah of your life, but the last hurrah of one of your life stages. Because these stars are not technically dying when they go supernova. They're just moving on to the next stage of their life cycle.
And it's not like we stop looking at them or stop caring about what's going on over there.
Yeah. Okay, so Corinne, what's your last hurrah gonna be? And for what stage of life?
I got as far as writing the question. I think there's something really fun about leaving your, not necessarily your 20s, but the kind of phase of life where you don't know what's going on and you don't know where you should put your energy or what you should do, and you feel very overwhelmed. And I have felt a lot more settled in the last few years of my life. Yes. And I don't think it's directly related to not being in my 20s, because I'm newly in my 30s, but there's just something about that era that looking back, it's oh yeah, I would throw one big party and that would be the last one. Even now when it's going out to dinner with friends or something, I'm and now it's time for me to go to bed. And I never would have done that earlier in my 20s.
Good for
so I think
you.
It would be some kind of specific party that's this is the last one I'm gonna do, and nobody gets hurt. And we just have fun.
I like that you had to specify nobody gets hurt.
Yeah, I think I can't even tolerate. Honestly, I can't even tolerate that kind of party now.
Yeah. Oh, I like that.
But that's a phase that I could graduate from.
I love that for you. All right, I've had time to think of my answer while you're giving yours. This is no secret to the internet. I was dumped a year ago, almost. In October, it will be a year. And since then, I have just been just casually dating. I did not want to be beholden to anyone but myself and my cat Cosmo. But I did give myself a year and a day as a time limit, after which I would be open to actually dating again. And so I think that my last hurrah, something that I am low-key really considering doing, is throwing a short-term open to long party, because on Tinder the different ways that you can specify what you're looking for is short-term, but short-term open to long, or just looking for my long-term partner. And for a year and a day I'm just at short-term, but after that I will be open to long. And so I kind of want to throw a party, and the messy part of me really wants to invite everyone that I've casually
I was going to say, you invite all the matches.
I invite all the matches, but then I just invite my friends, and they all have to bring someone who they think I would want to date.
That I like.
Yeah.
Would those people know that that's why they're there?
that's up to them, to like my friends to decide. You know what? I don't want to have to make that kind of decision.
There was some New York Times article or something talking about a Tinder party, and people would like bring their matches there, but everyone would bring their matches, and it wasn't like we're there together, but like we are, but we can talk to other people at this party. I was like, oh yeah, that's fun.
Oh, I love that. Yeah, so that would be like my last hurrah of staunch singledom. Love
that. That's really fun. And then we can continue to study you.
Great. Please do. I love being studied. Actually, that's not, I hate being perceived.
No. Oh my
when
God,
I am
same.
not talking about science or myths, I do not want you to know I exist.
That was the hardest part for me of living in a new city outside of New York, of like getting recognized at the coffee shops all the time. I'm like, no, don't know who I am. I want to invisibly move through this world.
Anonymity is nice.
And I can like flick it on and off.
Every bisexual awareness month, which I think September is, I'm like, oh no, do not be aware of me,
I'm not in the mood to be witnessed. Yeah, that's me.
Ugh, all right. But like, no matter who is perceiving you, and if you don't want to be perceived, like, you can really escape to a canyon and there's not anyone else around.
Nobody's
but, like,
here.
No matter how much you want to be perceived, you are still space.
You are.
Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.